Good afternoon, or good evening to those of you in Europe, and apologies to those of you in Australia. Welcome to Session 9 of the ESIG 2020 Fall Technical Workshop, being held online on Tuesdays and Thursdays during the month of October and into early November. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As with so many things we were planning to do in person this year, our plans were derailed by the coronavirus, and here we are online again. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We will have 3 individual presentations of approximately 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we are doing with all our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG27, ESIG27, as the event code to ask your questions. Please be sure to indicate the person to whom you are addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep your questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG27 as the event code. Session 9 today deals with a very timely topic, system planning considerations for high variable renewable energy penetration. System planning is an increasingly dynamic and exciting area to be working in these days, as plans change quickly to keep up with the new reality with such a quickly changing landscape. Today's session will be chaired by Bruce Tsuchida of the Brattle Group with his colleague Sasha Kuzura, also of the Brattle Group, serving as co-chair. Bruce is a principal with Brattle, providing consulting services and expert testimony to an international range of clients. Sasha has a power systems engineering background and is also a consultant at Brattle, which is a longtime member of ESIG. Bruce is a frequent participant in ESIG workshops, and we hope Sasha will become one too. We look forward to their continued participation. Bruce and Sasha, we appreciate having you here, and I'll now turn it over to you, Bruce.
First and foremost, everybody, welcome to this unusual form of the ESIG meeting that you would pretty much look forward to meeting in person. Unfortunately, the times don't allow that. For today's session, we have 3 distinct presenters that discuss the system planning considerations for high variable and renewable energy penetration. We'll start with Varun Sivaram, who will talk about what's going on in India. We'll then move over to Clyde Loutan, who talks about what's going on in California ISO, and finally, summarize the study approach that Jimmy Nelson at E3 has taken to model California. So with that, I would like to first introduce Varun. Varun Sivaram is on the faculty of Columbia University Center on Global Energy Policy, and he was previously the Chief Technical Officer for Renew, which is India's largest renewable energy company. He was also the Director of Energy Program at the Council on Foreign Relations. So he's got a lot of experience, and he's wrote a bunch of books as well. His books include The Training on the Sun, Digital Decarbonization, and his latest book is called Energizing America. He's a physicist by training and holds a PhD in condensed matter physics from Oxford University. So I'll introduce the other 2 as we go through their presentations, but let me hand the mic over to Varun now.
Great. Thanks so much, Bruce. I hope everyone can see that, and if not, I hope someone will just flag me. But I've just shared my screen here. That Thanks so much. I'm thrilled to be here. ESIG is a fantastic organization, and I think that the challenges that you're considering, a high renewable energy, a high variable renewable energy future, are challenges we will have to address today, even though the brunt of these challenges will really only hit us in a decade or two. So I want to talk to you about the view from India, which many of you, even though you're deeply steeped in the field, may not be intimately familiar with. But India poses, perhaps in my opinion, one of the world's greatest challenges for integrating variable renewable energy at the highest penetration around the world, and on severe constraints when it comes to political economy, the constraints of the grid, and the constraints of the markets. And my thesis is that over the next 10 years, India's investments, not only in building renewable energy, but in integrating variable renewable energy onto the grid at high penetrations, India's investments in the next 10 years are going to make or break its energy transition. And in turn, India's energy transition is going to make or break the world's fight against climate change. It is quite possibly the most important thing we could be working on. And I'll tell you a little bit from my experience after having spent a couple of years in India at India's largest renewable energy company. So today, I think I'd like to talk about 4 things. I'll probably only get to 3 in my allotted time. The first is I'll give you some background context on India. Second, I'll talk about some of the challenges that the Indian market poses for integrating high penetrations of renewables. And third, I'll talk about the actual technical integration challenges. The fourth section on opportunities, we may get to later on in the Q&A section. Let me first start by saying that the power sector is critical to India's clean energy transition. To set the stage, India, by the end of this century, could account for more cumulative emissions between now and the end of the century than any other country on Earth. So if your goal is to abate carbon emissions and combat climate change, your number one port of call should be India. And that's surprising to a lot of people who look at China, for example, and they say, well, China is the world's largest emitter. Well, if you look at cumulative emissions between now and 2100, and you look at India being one of the fastest growing economies in the world with no signs of its carbon emissions peaking, India is the number one place to look at. And decarbonizing power will be the number one thing for India's energy transition. As you can see from this graph, power will occupy the largest share of emissions, industries a close second place. But as power increases and we find ways to electrify end uses in India, it'll look different than in other countries. You'll have electric 2- and 3-wheelers, for example, rather than Teslas. As we find ways to increase the use of clean electricity, India could very well turn a corner. Now, traditionally, the power sector in India has been dominated by coal power. Last year, coal power was 3/4 of India's electricity generation. Recently, just in the last decade, 2010 to 2020, there's been this slow rise from a macro perspective in renewables. But to be clear, renewables have enjoyed extraordinary growth rates in the last decade. So the Indian government set this remarkable target of 175 gigawatts of renewable energy by 2022. They may not meet that actual target, but they'll get pretty close. And that in itself is an accomplishment. So quietly, India's renewable energy sector has become one of the world's largest. In 2017, for example, India was the world's 2nd largest solar market, and it's around there in the last couple of years as well. So right now, coal dominates the Indian power sector. That may not be true over the next decade, and that's why I think this is such a critical decade for India, one that will make or break its energy transition. Because India set a goal that by the end of the 2020s decade, so by 2030, it wants to have roughly half of its electricity generated from clean sources. And the largest source, as you can see here, is going to come from variable renewable energy, solar and wind. And so if India can meet this large target of 450 gigawatts of renewables by 2030, it's really a stretched target, would be totally unprecedented around the world. Then you could see that historically coal-dominated sector give way to a large penetration of renewables. By 2050, and this is data out from today's Bloomberg New Energy Finance, New Energy Outlook in 2020, by 2050, India could have one of the world's largest shares of variable renewable energy. If you're looking at this graph, you can see that India is higher, it's that purple line, it's higher than China, it's higher than the United States. It's really only lower than a few European countries that have idiosyncratic characteristics. But India will be the largest economy with the largest amount of variable renewable energy by 2050 if if these trends continue. And that's based on India's, vast endowment of solar resource, for example. So it's really a special place. Just zooming in on that a little bit, there's not only will India have a large penetration of renewable energy, but that renewable energy has to meet an enormous growth in incremental load demand. If you look at that, from 2020, where we're roughly 1,000 terawatt hours, to 2050, where we've quintupled electricity demand, renewable energy is going to make up most of that incremental demand, if not all of it. Now, that in itself qualifies India as a fundamentally different case from developed economies. You look at the United States, for example, decarbonizing. India is very different because if you just hold coal at bay and it falls slightly, you will really have accomplished the most important work, which is meeting incremental demand with renewable energy. I mean, a fascinating statistic is that 70% of India in 2030 hasn't been built yet. That urban infrastructure is going to be built. Folks will be moving into cities, and India will become the world's most populous country by mid-century. On the right-hand side, you can see what a high penetration of renewables in 2050 does for your load curve. You can see on any given month, solar and wind are making up the vast majority of your generation. In India in particular, folks don't know this, solar is cheaper to build in India than anywhere else in the world. And that's a testament both to India's resource endowment, but also to the brutal cost-cutting auctions that have driven solar prices down in India. So this graph from IRENA is particularly interesting to me because I look at it right in the middle. You can see the chart, you can see the bar for the United States. And as you can see, it's roughly $1,200 per kilowatt. India is half of that cost. Half. It is half as expensive to build a solar plant in India than the United States. And the reason we don't see that borne out in the ultimate price is because the finance cost is particularly high in India based on various risks that I'm about to talk you through. But when it comes to the fundamentals of building solar in India, we see a tremendously low cost and high potential. And, a lot of the reason for this low cost is this auction process. India has viciously competitive auctions. And so, I lived this. I've been in that room as our company has won auctions and lost auctions. What I want to say is that India can sometimes get a reputation for having, shoddy, second-rate craftsmanship or like cutting corners, et cetera. It's absolutely not true. I mean, our company, Renew Power, did complex load flow and durability analysis before making any mounting decisions. Our bill of materials is highly optimized, but it's also prioritizing 25-year operation and beyond. So I think that not only has India realized low costs, but they've rationally realized low costs. And it's an example for the rest of the world to follow, really. Now, that doesn't mean India doesn't have its share of challenges. I'll start with the market challenges. This is a complex set of charts. Don't look at this org diagram. But the only thing I want to show here is that most of the colors represent public entities. India's power sector is largely controlled by public entities. Sure, there is some upstream competition in generation, but T&D, state-owned, state-controlled. The federal government plays a large role as well. And so because of this historic, basically illiberal set of markets, you don't have very liquid markets for trading electricity. Just less than 10% of electricity is traded on any given day. Most of it is tied up in these highly illiquid long-term contracts. That's just the way the sector was set up, with these large coal power plants signing long-term PPAs with distribution utilities that are state-run. And so India's been making baby steps toward liberalization, but the markets in India work very differently from those in the United States that we might all be very familiar with. What I'm showing you here is the obvious efficiency gains that you get if each individual distribution utility wasn't tied to a long-term contract to each individual generating company or generating station. And that's self-evident to folks here in the United States who work in these markets. In India, we're making baby steps toward real trading of most electricity. It'll start with shorter term than longer term, but eventually we will replicate day-ahead and real-time markets in India. It will just take a long time. And as you can imagine, that makes it hard to most efficiently use the resources that you have at hand. the diversity of coal power plants and low capacity factor solar and kind of medium capacity factor wind and putting it all together and harnessing the few gas peakers that we have in India. So that's a real challenge in India. The other set of challenges I want to quickly touch on, and then I'll pause and maybe we can talk about technologies later on, is that there are going to be real integration challenges. Now, by 2030, if we don't accomplish the Indian government's goal of 450 gigawatts of renewables, we just accomplished 300 gigawatts, it's probably going to be manageable. India's grid is one of the world's largest synchronous grids. It actually has a fair amount of capacity to integrate renewables from around the country. There's a lot of geographic dispersion, and as a result, if you look at the graphs here, for example, on the bottom right-hand side, the integration challenge will be large, but it won't be insurmountable. These are peaky generation profiles that can be accommodated. And as you can see on the left-hand side, much of the solar is going to be in the south and the west, as is much of the wind. And so you're going to see exporting regions from the west and the south and importing regions in the north and the east. 450 gigawatts, though, the government's target, and what I call the culmination of this critical decade of the 2020s, that's going to be a different story. Up in the top row, you can see what a high renewable energy generation week looks like. Now, Bloomberg projects this will happen in 2034, but the Indian government, if it has its way and meets its target, it's going to meet that in 2030. And that is a tough duck curve to get around. We're going to hear from the gentleman who actually created the duck curve, and so I'm not going to steal his thunder, but India is going to go the way of California with a very pronounced duck curve. Now, there are some mitigating factors. In India, it's a hot and in many cases humid country. Air conditioning demand is going to surge, especially because most people don't have air conditioning. Less than 5% of people have air conditioning today. And so as the middle class grows and people move into cities, they're going to want air conditioning. And air conditioning nicely lines up with solar generation. And so you can see that by 2034, according to Bloomberg, the peak in electricity demand is actually going to be in the middle of the day. And that's different from some other Western developed markets. And it's going to line up very nicely with solar. To be clear, you're still going to have an evening peak. You're still going to need to do other flexibility measures. The coal fleet is a big liability in India, but it really could be an asset. What I'm showing you here is that on the left-hand side, the size of what could be stranded coal assets will rise. And on the right-hand side is a chart showing you from the Climate Policy Initiative that you can actually make money if you run a coal plant flexibly in order to compensate or buffer the intermittency of solar and wind. So India's got to find a way to use its enormous coal fleet to balance renewables, and it should be shutting down really old coal plants. It certainly should not be building any new coal plants. They won't make any money, they'll be stranded, and they probably won't play a useful grid balancing role. And finally, I'll just mention that India does have a strong grid, as I mentioned, but the levels of investment in the grid, which were strong all of the last decade, suddenly fell off a cliff in 2019. And 2020, as you can imagine, in COVID times, India stopped investing in its grid. And that's terrible because what we really need is a super strong interstate transmission system across India that's going to bring solar from, the sunny deserts of Rajasthan. And we also need intrastate transmission investments as well, and we're going to need distribution investments all the way up and down the chain. So that will be a critical thing for India to really meet its goals. I have some other slides, but I think I'm largely out of time. So I'll close by saying, I hope you check this out. This is shameless self-promotion, but very recently I gave a TED Talk on what India's energy transition could look like. And this critical decade is going to make or break, frankly, the world's fight against climate change. So I hope you guys take a second to watch the talk. It's just 10 minutes and walks you through what India can do on power and on all the other sectors as well. Thanks so much for the time. I'm going to stop sharing and hand it back to Bruce. Appreciate it.
Well, thank you, Varun. I hope that was useful. I would like to hold the questions until the end unless people have very, very pressing clarification questions. Sasha, do we see any?
We do not see any pressing clarification questions, so all the rest will hold until the end.
Thank you, Sasha. Then our next speaker is Clyde Loutan. As Varun said, he is the inventor or the developer of the duck curve that everyone knows. Clyde is the principal engineer at CAISO and has focused on power system operation performance. He's been the principal investigator for several technical studies on renewable integration. And before joining CAISO, he used to work at Pacific Gas and Electric Company in various capacities such as real-time operations, transmission planning, and high voltage protection. Clyde will be talking about what happened in California ISO, and especially about how he dealt with the ancillary service needs. Clyde, please take it from here.
Thank you, Bruce. My presentation today is going to cover operational challenges, what it is we see on a day-to-day basis and how do we continue to integrate renewables on the grid. Before I get started, I'd like to say, ESIG, you guys are doing some wonderful work here for the industry and keep that up. So my very first slide is looking at California's aggressive energy and environmental policies. So by 2030, 40% of the greenhouse gas emission needs to go back to 1990 level, and by 2050, that bumps up to 80%. In terms of renewable, California is trying to be a zero carbon free state by 2045 timeframe. That's going to create some operational challenges, and we need to address those before it does become a problem. On isolated days, we have seen, almost, there was one day for 1 minute, 99% of the load was served by carbon-free resources. So we know it's doable. It's just we need to figure out how to do it. So decarbonization also is creating a lot of opportunities, and that's something to keep in mind. Opportunities not only at the grid level, but also on the distribution level. This one slide here, we can talk about this half a day. And what it really says is, look, on some days, you rely on the gas fleet quite a bit. So this was actual operating data for 1 week, consecutive days. And you can see on the 14th, which is the third peak day, we had to rely a lot on gas plants. We had to rely a lot on wind and solar. And with about 18,000 megawatts of wind and solar on the system, the maximum production we saw was 3,800 megawatts. So it tells you that right now we need to find a way to transition from the gas fleet. So be it things like storage, be it things like, wind, solar providing ancillary services, being able to be flexible. That's going to be very, very important moving forward. If you look at the chart on your right, this is during hydro spill conditions here in California. And what you can see is you have a lot of hydro, a lot of snow melt, and you've got to back that gas fleet really, really low, which is that orange at the bottom. And then we got some base-loaded plants. Well, what happens when you back the gas fleet really low? Now you got to rely on the gas fleet to provide all the ancillary services that you need. Because under hydro spill conditions, the ancillary services that you got from hydro is not there anymore, because hydro more or less is operating at its peak capacity, and being able to back down or being able to provide ancillary services is a challenge. So the takeaway from this slide is, moving forward, we need renewables to provide essential grid services to help you balance the grid, things like voltage controls, frequency control. And this is what my bulk of the rest of the presentation is going to focus on. Before I jump into that, on this next slide, and you guys are going to have these slides, but it just tells you about the operational challenges that we see today in California with the amount of solar we have. This is grid connected when I mentioned 12,000 megawatts, but we also have over 8,000 megawatts of rooftop PV, and that creates some unique challenges also. So during the middle of the day, we have more renewables than load, so you tend to see oversupply, and there are ways that we try to handle that because you do not want to tell developers after they spend millions and millions of dollars to develop renewable plants, you do not want to curtail these. So we're looking for engineering solutions. How can we minimize the amount of curtailments, right? So things like time of use rates, we think that can play an important role. So essentially, what we're trying to do is to raise the belly of that duck by a lot of different means. What it is we can do in terms of load shifting, load shaping. So, and then again, as I said, I like to hit on this is the dispatchability of renewable resources. So I'm moving fast on these slides here, and then this rooftop PV is also created some operational challenges. What I mean by that is currently you have no visibility on rooftop PV. So just think about controlling a grid or balancing supply and demand every 4 seconds, which is what we do in California, and you have no visibility on rooftop PV. So today, on a weekend especially, almost 30% of your supply you don't see in real time. So you tend to be reacting to, the variability, cloud covers, everything that's associated with solar production from rooftop PV resources. And why that's important? Because it also impacts system frequency. And in the U.S., when I say we, each balancing authority gets a benchmark as to how well you perform every minute. So every minute, we do a calculation to determine are we supporting the interconnection frequency or not. So we can get a little more into that later on, but that is one of the things that makes it very difficult to integrate renewables because you've got to control frequency within predefined limits that's set by NUC. So just jumping ahead, what's the ISO doing? The ISO is trying to share awareness to other balancing authorities. The more I think people understand the challenges the system operator faces on a day-to-day basis, that's the only way you're going to have, smart engineers coming out of school. You're going to have we got a lot of universities out there. They can help us solve some of these problems. So the challenges is huge. One point I'd like to emphasize here is integrating wind is a lot different from integrating solar. So the variability you see with solar on a system that's heavily integrated with solar resources, it's a lot different from what you see with wind. Wind resources, you tend to see geographic diversity minimizing variability. You just see the opposite with solar plants. So today, what we notice on our system, in 10 minutes, the system changes by between plus or minus 1,000 megawatts to plus or minus 2,000 megawatts. And that's huge. To deal with variability of that magnitude in 10 minutes when a huge part of your supply you don't see. So you tend to be reacting most of the time, and we're looking for ways now to, again, be proactive in solving some of these problems. So again, the takeaway here is renewables has to provide essential grid services. They must play an important role in integrating more and more renewables into the grid, and renewables needs to play an important role in decarbonizing the electric grid. These are some of the things the ISO is doing in terms of load shifting, load shaping. You can look at that when you get the slides. And the rest of my presentation, I wanted to focus this on how can we use wind resources to provide essential grid services. So what we did is we partnered with Avangrid Renewables. We partnered with NREL and General Electric to test a 131 megawatt wind plant to see what kind of services it can provide. And what we found out is wind plants or inverter-based resources can provide all the grid services that you need, and in some cases could provide those services a lot better. So if you look at this first slide, this is looking at a ramp rate on a wind resource. And two different ways you can operate here. If you look at the one on the left, it tells you, let's say you have a set point. So here we took this plant all the way down to less than 20 megawatts, and then we increased it back up to about 115 megawatts. Well, the way this plant could operate, it could meet end set point. So if you look at the set points, which is our V shape, when you look at the wind trajectory, you can see it was able to ramp down, it was able to ramp up to meet the end set point. Now, if you look at the right, you'd see a slightly different way the wind plants could operate. Same operates, but if you want the wind plants to follow set points, that same V shape, you can see it's two curves there. One is a blue, which is the set points, and how accurate this wind plant is able to follow a set point signal. So in terms of controllability, if you operate a market, if not, it can follow dispatch signals from a system operator very well. This other plot here shows you how well a wind plant could follow a 4-second regulation signal. And on the top left, you have the plant output, which is blue. The orange is the set points that we fed this every 4 seconds. And, you can see how well a wind plant is able to follow 4-second signals. In order to do this, you need to have some headroom. So the curve on the right, you can see the actual production capability of this plant. And then with the headroom, it could provide upward and downward regulation service on a 4-second basis, which is something you need to control the grid. When you look at the error in control at the bottom left, it's within 2%, which is, really accurate. And then the lower right is we compared different categories of resources, like combined cycle plants, like hydro plants, things like storage. But if you look at the green curve, or the green bar, it shows you a wind plant could follow a regulation signal or above 90% accurate with accuracy. Whereas, the other plants, they can perform, because they got rotated mass, around 60% or less. So it tells you, wind plants can perform very, very well. This plot here shows you how well a wind plant could provide voltage control. And again, the voltage set points is the bars per se, and then that blue wiggly curve is how well this wind plant was able to follow a voltage set point. So you lower that voltage, you increase the voltage slightly, and that wind plant was able to follow that signal accurately. The one I like is the plot to the right. If you look at this, that plant could produce reactive power at 0 megawatt output. So that blue line again is no megawatt output. So again, during any time of the day with no active power output, this wind plant could control voltage. On this day when we tested this plant, the voltage at the high side of that transformer was high. So we could only buck the voltages, and we bucked it. And then right about the middle of the curve, you see we were able to increase or get reactive power out of that plant. But again, this is very interesting in that even though the wind's not blowing, you can get voltage support from a wind plant. Now, what's really important here on this plot here is showing frequency response, frequency control. Wind plant, again, this is actual events that we had in the Western interconnection. So the blue is an actual frequency drop that we fed into the plant controller. And you can see how well this wind plant was able to increase megawatt output. And again, you need to have a certain amount of headroom available. So this plant was able to respond to that low frequency event very well. Thing to remember here is you may see a slight delay in the wind plant in responding. Well, it happens that this wind plant was not equipped with the software to operate faster. So GE has the capability to program a wind plant to operate much faster than this plant. We did not have the time when we did this test, but the capability to control your response time is there, and there's a light at the end of the tunnel where you're going to have controllability on these plants. This last slide I wanted to show you here is wind can produce frequency control in the transient time frame and then on a normal steady state time frame here. And you can change certain things at the wind plant, things like the droop setting, things like the deadband, pretty easily. The one on the left shows you response at 5% droop, 4%, or 36 millihertz deadband. The one on the right is 4% droop at a 4% or 16 millihertz deadband. You can see you get more response on a normal steady state operation with 16 millihertz deadband and a 4% droop. Reason why that is important is we're going to be relying on renewables to provide these ancillary services. And again, normal steady state is a challenge for us. And we can talk about that at the end. And then there's one last slide I'm not going to get into, but it really tells you that we need renewables to provide essential grid services for us to meet a low carbon grid and meet the aggressive environmental standards that policymakers are setting. With that, pass this on back to Bruce.
Thank you, Clyde. You guys heard the voice directly from the guy who invented the duck curve. That's a very rare occasion. Sasha, do we have any immediate questions from the audience?
There are no immediate questions, but we got them all queued up for the end.
Thank you, Sasha. The last presenter is Jimmy Nelson from E3. E3 is a consulting firm, and Jimmy advises utility system operators and state agencies on the operations, economics, and planning of the electric systems, especially with large amounts of variable renewable energy resources. Interestingly, Jimmy began his career in energy working to make solar panels when the solar panels were much more expensive. So bringing down the cost was one of the main drivers and one of the main barriers to adoption at the time that Jimmy was working there. Now, more than a decade later, he's helping clients understand how things work and how to manage it, the renewable source energy. So Jimmy will be talking about how to model the system. So Mike goes to you, Jimmy.
All right. Thanks, Bruce. Can you hear me? I will assume that you can. So I'm going to walk you through in about 10 minutes a 3-year-long planning process that E3 has been involved in with the California Public Utilities Commission. E3 is the consultant to the Public Utilities Commission and helps especially with resource modeling. I was the technical lead for a lot of the capacity expansion modeling on this engagement. As you might expect, I'm speaking as a representative of E3, not of the Public Utilities Commission, and everything I'm saying is kind of in the public domain, so no surprises there. The California Public Utilities Commission regulates about 80% of California load and covers the service territory of the California Independent System Operator. So you can think of it as basically helping to plan the CAISO system. And the first part of the planning process is to really, for the CPUC to kind of outline the greenhouse gas reduction target that they'd like to look at. And the main focus is the early years, the years that really, you can make pretty certain investment decisions. So we focused on the years between 2020 and 2030. And one of the biggest kind of levers that the modeling looks at is what the greenhouse gas target should be in 2030. We looked at 3 different targets, and the CPUC ended up adopting the red line as their planning target. And then, to address the risk of stranded investments in the long run, we look at a much deeper, much longer term greenhouse gas target out to 2045. A brief overview of the IRP process. So, the first step is to kind of look at the greenhouse gas target, figure out how many reductions the CPUC wants to try to take on for the electric sector. Then the CPUC creates what they call the reference system plan. The portfolio for that is designed using E3's Resolve capacity expansion model. And then the CPUC sends that reference system plan along with some planning information to the load-serving entities. There's roughly 40 load-serving entities in under the CPUC's jurisdiction. So there's quite a lot of different entities that have to then plan their own system using inputs from, their own situation plus the reference system plan. The CPUC then, once they've finished planning and submitted a plan to the CPUC, which was, I think, in September of this year, the CPUC reassembles all 40 plans and kind of looks at it to make sure it still makes a coherent whole. And if there's any deficiencies that arise, the CPUC can order procurement if necessary. And then it's a cycle that repeats itself over and over again. So, we would do this again. Drilling into the modeling a little bit, I think it's probably no surprise to most folks on this call that a system with a lot of wind and solar and storage, you really need to look at how the system operates to figure out how you would want to make investments in that system. That didn't always used to be the case. A lot of times you would just trade off operational costs and fixed costs and, figure out if you wanted to build a peaker or a baseload plant. But we designed the resolve model to basically, sort through different operational questions and use that information to make resource plans. Another really important consideration for planning a system with high levels of energy-limited resources like wind and solar and storage is, how much do those resources, how much can they reduce your demand for other dispatchable resources in California? This is largely gas plants. So we, at least at a high level, have included a number of different dynamics related to the peak capacity contribution of solar and wind and storage. I think it should be familiar to most folks that as you get more and more solar in a power system, the net peak starts to move to the early evening and more solar doesn't help you as much anymore. The same impact happens for storage. Storage flattens the net peak and at some point it becomes so flat that more storage helps less and less. And then there's a combined portfolio effect where at least in California, the solar can kind of squish the net peak into a fewer number of hours, which gives the storage more capacity contribution. So at least at a high level, we've included these dynamics in the modeling we've done for the CPUC. Going to the kind of the results of the portfolio and the portfolio that the CPUC selected as their reference system plan, I'm showing here the incremental resource additions between 2020 and 2030. All of the existing grid, the stuff that's there in the ground right now, isn't shown. So this is just the new stuff that would have to be built. And I think the big story here, which is also probably no surprise, is the level of battery growth that we see in the next 10 years. So, there's roughly a gigawatt plus or minus of batteries on the California grid today or in the near future. And it's looking like the reference system plan would have around 10 gigawatts by 2030. So that's, in my mind, pretty transformative growth. There's also significant build out in solar resources, but the solar industry is already pretty established in California. So I wouldn't call it quite as transformative. It's just kind of incremental growth, albeit with a huge number of gigawatts. And then there's some other diverse resources like wind and pump storage and demand response that are represented in some magnitude, but not that large. And then one other important thing to note is that we included in Resolve the option to not retain contracts with gas facilities. The CPUC can choose to order or choose to kind of provide direction not to recontract with gas plants if they so desire. But the modeling at least implies that the least cost solution would retain all of the gas plant capacity through 2030, even while building quite a large stack of clean resources. An IRP wouldn't be complete without looking at some of the alternative realizations of the future. In this case, we looked at, the question, what if battery costs end up being higher than projected? Every year we get a new round of battery cost projections. They always look different than the previous year. And so, you really want to make yourself sure when you're investing in a lot of batteries that that's a good decision under multiple different criteria. So we performed a sensitivity analysis where we increased the battery cost trajectory significantly and saw that the model still picked a bunch of battery capacity, but also diversified the portfolio significantly. So, it looks like if you believe these modeling results, California is headed for some significant battery growth within the next 10 years. I teed up the question of the role of resource adequacy in the previous slide, and here we kind of get to the results of that. On the left bar chart, you see the installed capacity, the nameplate capacity of resources, and on the right, you see the resource adequacy, or what you might expect that resource to generate at peak. For solar, kind of unsurprisingly, all of the solar generation that's on the system has shifted the capacity needs into the early evening hours where solar standalone can't really get to it. The battery story is a little bit more interesting. So we had Astrope Consulting, which runs the SIRVEM model. They took the CPUC's implementation of the SIRVEM model, which is an industry standard resource adequacy model, and they created this battery storage marginal capacity value curve for us, which we implemented in Resolve. And by 2030, you can see that the storage is starting to provide less than 100% of capacity value. In other words, it's starting to kind of flatten the peak so much that it's hard to meet additional peak needs with storage if it's, only, say, a 4-hour battery. By 2045, which I don't show in this plot, but I thought it's just kind of interesting, that is really played out, and the marginal capacity value of storage is somewhere south of 10%. So, I'm kind of one of the people that when we run a model and then it produces some results, everyone kind of wants to know, why did the model pick what it picked? And so when I get asked that question, I like to go and look at the marginal costs of the different constraints in the model. So to kind of say that in less model-heavy terms, you can think about a high greenhouse gas abatement cost in a certain year means that really reducing greenhouse gases is driving portfolio selection, is causing the portfolio to appear as it is. By the same token, a low greenhouse gas abatement cost means that other things are driving what the portfolio looks like. So in the reference system plan, which is in gold here, and 2 other different greenhouse gas targets, you can see a dynamic that we see across a lot of different model runs where the greenhouse gas abatement costs look low in the near term because a combination of tax credits for wind and solar and peak capacity needs for batteries end up driving clean resources in, and those dynamics make the marginal cost of greenhouse gas abatement low in the early years, and then that shifts into the later years where the cost of reducing greenhouse gas emissions more becomes higher. So this gets me to kind of, a question which I think we're interested to explore more in the future. You really see the portfolio being driven by different factors in different years and across different scenarios, and it leads you to wonder, what is the future going to look like? So to think about the future, first let's go back to the past. In the past, you would install resources and cover your capital costs and fixed costs largely using energy and ancillary service margins, so you'd make some money in the energy market, and then maybe there was some missing money, maybe the energy market revenues didn't fully cover your costs, and so you would bid your resource into the capacity market, and that would cover the missing money. Well, in the future, it's very well possible that the green or clean attribute of a resource might cover a lot more of the fixed costs than it has previously. It's kind of a new value stream in a lot of ways. But I don't think we really know for sure whether resources are going to be mostly driven by capacity needs or clean attribute needs. And to kind of wrap it up with just an example, wind and solar are going to tend to do better in a market driven by clean attribute needs, and maybe batteries, which have at least initially a high capacity value, might do better in a world with more peak capacity needs. I'll close with some links that you can follow. I think this presentation will be recorded and posted, so you don't have to look at them now, but I'll note that you can download and run the resolve model yourself. It's a Python code that you can download, and it's free for anyone to use. So with that, I'll thank you, and pass it back to Bruce.
Thank you, Jimmy. I will actually pass the mic over to Sasha, who has been collecting all the questions that came in. Sasha, do you want to take it from here?
Yes, of course, Bruce. Thank you, everybody who has submitted a question and voted for questions. So without further ado, we'll start with a question for all of our panelists. The question is, what's the bigger challenge to planning a high VRE system? Technical balancing and operational challenges, or institutional arrangements, or coordination and maybe market design, non-tangible things like that?
I'll start. I think the answer to that question depends on where you are. And so I will answer that the answer in India quite strongly comes down as the latter, institutional constraints. So for example, the biggest risk in India of its clean energy transition is probably not the technical capability to balance, an intraday operation, but rather the fact that the distribution utilities are largely bankrupt. Many of them are bankrupt, and they're insolvent, and as a result, they can't pay for the power that they need to procure, and that leads to severe load shedding. It degrades the investment environment. So it's institutional concerns like that. Another one that I talked about in my part of the presentation was the fact that the market is so illiquid, or there isn't really much of a wholesale energy market, and that makes it hard to dispatch efficiently. So I think that in a developing, emerging economy like India, institutional constraints need to be solved first, and that's going to open up the possibility to do some very intelligent operational balancing and things. Of course, they're both important, but I personally would prioritize the institutional part.
So this is Clyde. I agree with Varun, but each system is different. But I think we need to make a lot of changes, like on market designs. We also need to make a lot of policy changes on technology changes. So the way we used to operate is going to have to change if we would like to achieve these high or aggressive renewable goals. Like today, as I said, we balance the system every 4 seconds. But you do that through a centralized control system where you can send signals out to units on let's say, regulation, and they can move. But we've gradually moved into a system where you're going to have so much renewables, things like plug-in electric vehicles, a lot of storage on the system. We need to think, how can we get these resources to help us control the grid? And that's going to be a challenge. The traditional way is no longer going to work. Centralized control cannot really do this. We need to look at ways to control through, let's say, frequency down the road. That's going to become a challenge. So all three, from the policy side, market changes, because today when you dispatch units through a market, the market does not see system frequency. That's a huge challenge. So what I mean by that is you could tell a dispatchable unit to go from 100 megawatts to 120 megawatts. What happens if the wind kicks up or the solar kicks up? You do not really want that unit to go to 120 megawatts. You want it to either stay at 100 or back off. So we need to think, how do you feed back actual system AGC problems like area control error or frequency back into your dispatch? So it's a slow of things we need to do to make everything work.
I'll just add quickly that I think transmission planning is a really big question mark. The timeline to build a new transmission line is on the order of 10 years. And if we're planning for 2030, that means we might need to start now. And there's a lot of institutional challenges there. I don't know if it's the biggest one, but it's certainly a big one.
Yeah, I agree with that too, Jimmy. One last point I forgot to mention is I think from an operational standpoint, the biggest challenge, systems operators face today is not under contingency conditions. So today you have a lot of planners look at an N-1, N-2 situation. We do a lot of studies in this area. But to me, the biggest problem that you see right now with all of these renewables is N-0, which means you cannot deal with the natural variability. You need, and as I said, you need to balance the system every 4 seconds. How do you see that ahead of time? How do you control it? So two things that really impacts you need for flexible capacity on the system. One is forecast. And I would say if you have, let's say, a crystal ball and you can predict that forecast, and you've got four big variables now, load, wind, solar, rooftop PV, and load. And if you could predict that, let's say you could predict that accurately for the next 5 minutes on an average, you still got to deal with the natural variability like clouds, humidity and other things. So the natural variability that we see, as I said, it's in the thousands of megawatts. And how do you deal with that? It's a huge challenge.
Thank you. Oh, sorry, was somebody about to speak? Well, thank you for those answers, gentlemen. And now we have a couple of minutes left to ask a couple more questions. So I would like to ask each of you an individual question based on the popular questions submitted through Slido. So for Clyde, many people have been wondering on slide 10, in which you show the accuracy of the battery resource following the AGC signal as lower than that of the wind and solar resource. Would you mind clarifying why the battery accuracy was lower?
So currently, the batteries, my guess is they can perform as well as a wind or a solar plant. When we did that analysis, we had less than 100 megawatts of batteries on the system, and they were still trying to fine-tune the controls, on the batteries. So right now, my guess is when we update the battery response to AGC signals, they're going to be comparable to wind and solar, which is closer to 90% or more.
Okay, thank you very much. And the next question is for Varun. The question is, how do you reconcile a weak distribution system with high build-outs of VREs?
It's a terrific question. I mean, most of India's renewable energy targets are going to be met with centralized renewable energy. And at the end of the day, even if you do a great job of building out your interstate transmission grid, at the end of the day, if customers are only getting power for some fraction of the day because of the weakness of the distribution grid, you failed if all you've done is build centralized renewables. So that's why, a top priority is going to be distribution utility reform. I also think there's an important role for distributed clean energy to play in India. And I'm not really talking about residential rooftop solar, which will play a tiny role in India. I'm really talking about what I think of as mesoscale, kind of hundreds of kilowatts or megawatt scale solar that can be sited on ground mount, for example, in order to get your economies of scale, but can be put close to the load centers. And I also think that there is scope for innovation in how you run the distribution grid. I advise a company, Camu Energy, that's one of the members of ESIG, and I think that they're doing interesting work in developing methods to orchestrate the distribution grid of the future that apply equally well in the U.S. as well as in India. And just because I know we're about to run out of time, I'm going to say something completely separate, which is after listening to the two other fantastic presentations from Clyde and Jimmy, I just want to make the point that renewable energy developers like us in India or like those in the United States need to have incentives to invest in the infrastructure for their renewable energy plants to provide the ancillary services or other grid services that, for example, Clyde's talking about in the CAISO system. In many cases, when we build a plant, we do automatically already have the infrastructure there for our inverters to act in ways that help our plant provide services. But there's an additional layer of design thinking and intentionality that goes into designing a plant that unless the market gives you that incentive, you're not going to build it out. And, when we made the decisions on whether to use string inverters or central inverters for our solar plants, there are a lot of interesting technical capabilities that string inverters give us that we often, in my opinion, under-prioritize from a system needs perspective. So I think that for developers to really build sophisticated renewable energy plants, make the full use of functionality, market signals are going to be necessary.
Thank you very much, Varun. And the last question is going to go to Jimmy. And the question is as follows. Planning uncertainty leads to different operations, and system operations are important to planning. So when you're modeling capacity expansion, how do you address this conundrum robustly?
Yeah, let's see. So in Resolve, we have a kind of an hourly varying uncertainty reserve that we force the model to supply in all of the hours that we model. So, it doesn't quite fully update with the renewable portfolio, but it does kind of get you into the right level of megawatts of headroom and footroom you need to operate the grid. And I think, as we learn more about how to operate a highly renewable grid, we'll have to update that as well. And so I think that's the main way we capture operational uncertainty, other than just, we try and use time synchronous data in our planning model. So we make sure we're actually modeling kind of real incidences of load, wind, and solar forecasts. Back to you, Sasha.
Okay, thank you so much for that answer. And this brings us to the end of our session, so I'm going to pass it back to Bruce. Thank you very much, gentlemen.
Presenters and everyone who joined us. We will keep the records of the slide of questions and ask the presenters to provide answers, which ESIG will share with everyone here. In the meantime, I'd like to point out that there's 3 more sessions left for ESIG. One is on Thursday, talking about offshore wind, and that'll start at 2 p.m. And then in another 2 weeks, there's one session on Tuesday at 2 o'clock that talks about advances in system operations and market design for high renewable penetration systems. And then finally, on Thursday, November the 12th, there's going to be a session on generation and storage technology. So stay tuned and please join us in those sessions as well. Thank you for the participation. We hope that you all stay safe, and we look forward to seeing you in the remaining sessions or in person in the very near, hopefully, future where everything is settled down.